very autofocus.
Yeah. Or maybe just YouTube, or I don't know, but it was like, yeah.
Feel free to check if it is focused or not. Unfortunately, I cannot be on the other side. So,
Yeah.
is it focused?
Yeah, it's on.
All right. Yeah. But the important part is that you hear me in the presentation. Anyway, today we will start by talking about the first linear transformation that will actually be used in order to help us for feature selection, and it is principal component analysis. So today we will learn what principal component analysis does and what its properties are. And on the next lecture, we will go deep inside the algorithm and see how like line by line we have to implement it. But this lecture is plays in a very important role because it helps you to understand what really PCA is. Now, in order to conduct this lecture, as I mentioned, we will use board today, so no slides. You may need to write down this stuff, or we have hopefully them on the YouTube, so you can watch them. Principal component analysis have been driven from a very important mathematical property which is called IN problem, the IN values. If you remember last week, I told you that please go and read the information about IN values. So if you don't know what IN value is, that means you didn't read it. But again, I will try to quickly review all the materials that we need to do, and you need to know. So let's start by, today we will talk about principal component analysis, but we do it over an example, so you learn through the example. Imagine we have these 2D data. Imagine we have this 2D data, which is sampled from a distribution. And we call the first axis, I call it x1, and the second axis, I call it x2. So this is feature 1, and this is feature 2. So we have two-dimensionality, which means that we have two features. So we stick with these two dimensions. Now, so our talk is about principal component analysis. And in short, we call it PCA. Now, what PCA tried to tell us, PCA tried to tell us in which direction we will have the maximum variation. So PCA tries to tell us in which direction we will have the maximum variation. So if you want to put it into the word, it will be PCA find directions of maximum variance of data. So it means that if you pick one direction, if you pick one line, and we try to project all our data on that line, how we will have, or upon which line we will have the maximum variation. Of course, what is the easiest way? To pick the x1, the feature of x1, right? Let's pick the x1. If I pick x1 and I map everything on x1, what happens is this. Everything is varying on this pink line, isn't it? I mean, if I map all my data on x1 on the first dimension, you see they will come between these two lines. We don't have any data less than this or any data above this one. So what about if I map it on x2? If I map it on x2, it seems this is the region that I have all my data. Right? Here is the 2D example. What does it mean? I am projecting on x1 and x2. It means that for any of these black data, I am telling you that what is the distance of this data to x1 and what is this distance to x2. And if I know it, it means I know where is the location of my data, isn't it? It's called xy coordinate. It's called Cartesian coordinate, right? I tell you how far I am from x, how far from y, and then you can tell me where the data is. Now, looking at this data, can you tell me that, in your opinion, in which direction do we have the maximum variation?
It would be like on the diagonal.
Yes, it seems like the line which is diagonal, the line which is like almost 45 degrees, I don't know, 60 degrees, is the line which we have the maximum variation. So let me I have this line, and it seems that if I am mapping everything on this line, starting from here till here, if I map everything on this one, it seems I have the maximum variation. So PCA will help us in order to find all those directions which give us the maximum variation. Of course, this is the first thing that we want in PCA. So we can continue our sentence by writing down. I've written all my sentences so it makes sense when I'm writing them down. I have a potential of jumping between sentences. So this morning I wrote lots of pages for you. So PCA finds the direction to maximize the variance of data. So if we have to pick up a single direction in our example, we do it for 2D, but without loss of generality, you can consider it for ND. Okay? The reason that we do it for 2D is that I can draw it, you can visually see what PCA is doing. So I see the direction in our example such that if we project it onto that dimension, onto that direction, and on to that specific vector, and we compute variance then which direction results into maximum variance. We can start by projecting our data on its own feature. By contrast, we can project data on any vector that we like to.
Excuse me. Oh, it doesn't seem to be working properly.
It seems to be out of
No,
focus.
it's
It's
like-
going in and out all the time.
Ah,
It's trying to do something.
this is very good.
Okay.
The task of PCA is to find such direction which let our data to variate most. Why do we care to find a direction which our data is having higher variance? Why do we care about it?
Then it's easier to discriminate.
Yes. If the data is varying more, if I have more space to vary, it means that then I can have higher potential of discriminating it. When I have very narrow band to vary it means that I cannot discriminate well because our data will be very close to each other. So PCA help us to find those directions which if we project our data on that one, we will have the maximum variation.
Is that the,
Sorry.
is the gay pass?
Yes, yes, sure.
Is it and like is that the way also to like kind of reduce features as well, or?
We will talk about it towards the end.
Okay.
One of the properties of PCA is this data reduction. Now, feature reduction. If we have, this is a very nice set of data. It is an oval shape. And we know that if we have an oval shape, the highest discrimination or highest variation, change of variance happens if we are on the main axis. This is the main axis of this oval shape that we have. Now, so PCA will tell us, if I give this data, the first discrimination is on this line, or the first maximum variation is on this line, which results into a better discrimination. What about the second best line? What is the second best line which gives us better discrimination? Now, one of the cool things about PCA is that it not only provides us with the first best line, but it also provides us with the second and third, depends on the dimension of the data that we have, best lines which help us to maximize the variation. Now, in order to know what is the second one, you have to remember some property that we have with these ion problems. So I will use a few terms, and I will use this mathematical term, but I will also tell you that how we can interpret it into pattern recognition. So, like one of the constraints of PCA is it finds directions. So it finds the direction which we are maximizing the variance, but there is a very important property for these directions. It finds the directions that are mutually do you know what they are? Mutually orthogonal. is meaning of mutually orthogonal? In our example, or any 2D example, it means directions are, do you know what is the meaning of orthogonal in 2D? Perpendicular. The directions are perpendicular to each other. So, the blue line is the first, and the second one is perpendicular to this, and it will be, let's say, this one, the orange one. So, because we have two features, we will go to another two features, and these ones are perpendicular to each other. So this angle is 90 degrees. The first one, the blue one, the first direction is called first principal component, and the second one, the second direction, is the second principal component. I have written them in blue and orange color so you understand that they are corresponding to these two vectors that we have.
Does like we should count or order them in the other way, or
Now,
what is first and what is second?
Now, first means that take this one, project everything on that. All the data on that one. Then take the second one, project all the data on that one. And basically, what we do, look at this new one. It is a linear rotation of the original axis, isn't it? So PCA tells us, take the coordinate, I rotate it in a way that now if you project on your axis, you will have the maximum variation on each of them. So we will try to find such a coordinate, which if I project, I will have the maximum variation. Actually, right now, we write in a few properties, and you see that by this maximum variation, it means that we are minimizing some error, which I will tell you in a few minutes. So what is our aim? We have this coordinate, we have this data, we are not changing our data, but we want to change our axis, our coordinate in a way that on each of these axes, if I am projecting my data, I will get the maximum variation. Of course, if you change it, you will start to see new values, but new values of the same thing. Okay? New values of the same thing. Now, I have x1 and x2. With PCA, I am getting, let's say, phi1 and phi2. They are my new features. So I am transferring my data. I am getting new features, and I'm now manipulating those features. And a bit later, we will see how we can reduce this number of features. So, they are called the first and second component. Why we stop by the second component? Because we have only two features. So, if you have n, you could have n principal components. Here we have 2D, 2 dimensions, so we have two principal components. So, there are, I have listed a few important properties that PCA are introducing us, and we will write them down because we have to discuss about them. How these properties are helping us in order to have better discrimination or better representation of features. Let's put it in form of the cool things about PCA are Now, I will list them, and for each of them I may write a little bit of things. So don't be surprised, after 10 minutes I write number 4. You understand this is the continuation of these cool things. The first two, we already have discussed them. What was the first one? It maximizes the variance. Maximizing variance, i.e. finding directions in which the variance will be maximized. What was the second thing? These directions are orthogonal. These directions are orthogonal. And this results into, they are glue, it results into PCA is a global algorithm, and by global we mean all directions all the directions and all the new features. Look, this is a new feature now, new access. This is also another new feature. All the new features find have an big global constraint, namely they are mutually orthogonal. If two vectors are orthogonal, and if I project one on the other one, what do I get? If I project this axis, the orange one on the blue one, or x2 on x1, what do I get? A point. I do not get another vector. So this is a very important fact that we have to consider.
I'm sorry, how 2 and 3 differ? What is the meaning?
Now, when it is a global algorithm, it means that we can generalize it. It's not only valid for this case that we are drawing it. It's not only valid for, let's say, facial images. It's valid for any type of data that you have. That's why that if you go to Excel, you might be able to find the pieces, so people who are doing their statistics can use it. And it has been driven from the fact that all the vectors that are being driven by PCA are orthogonal to each other. And we will learn a little bit later how we can actually find all of these vectors. So all the properties are kind of a consequence of each other. Now, as a result of these three, we get the fourth cool property of PCA. And in order to write it down, I want you to look at it from this perspective. So, I have a black point in my black coordinate, right? And I am introducing a new coordinate. And I am telling you that all of these points can be again represented into this new coordinate. Is it true? Do I lose any of the points now?
No.
No. So it means PCA is perfectly reconstructible. You are not losing any information. You are transferring your information from the new coordinate to another coordinate, but you are not losing any of your information. So the fourth cool thing about PCA is it is pretty good reconstructing the data. In other words, we lose no information. Well, we were expecting to hear this, right? Because it is only a linear rotation of our axis. The original axes are perpendicular, are orthogonal to each other. These ones are orthogonal, so we were not expecting to see any loss of information.
Why is it only pretty good?
Sorry?
Why is it only pretty good? Or better?
Is there some points that you lose, or I guess you can basically
No.
like
No, with this you don't lose anything. You can make it to lose. We don't. This is the next step that we talk. But PCA, you can perfectly reconstruct all your data. You lose no information. We will talk about how PCA help us in order to lose some of the information which we don't care. But at the moment you can see we are not losing any information. It's just like you are looking at the pen from different angles. You are not losing any information regarding to pen. Now, one of the things is with the PCA, you can look at this axis, you know that it tells us, it tries to maximize the variation, right? And one of the cool thing is, it tells us, you will see in a few seconds, that when we are projecting our data on different axes that we have, it tells which of these axes are more important. In other words, PCA help us to represent our data based on its importance. When you look at the x1 and x2, you cannot say that which of these features is important. Well, this is a very naive example and you cannot really see. But if you have, imagine, n dimension, you don't know which of these features are important. But PCA help us to represent the data, again in n dimension, but based on its importance. And we will see why it's based on its importance. And it is the moment that we can come and say that some of these features are not important, so we can kick them out. Now, when you kick them out, it means that you start to lose information. But we will lose those information which is not very important. But principally, the principal component analysis reconstruct very good without any loss of information. But it also represents the information in the dimension which you can see that some of them are important, some of them are not important. We will talk about it in a few seconds. So, although in the new dimensions we have new values, if previously this point was 5 and 6, we know that the new coordinate it might be different number, so we have different number. But it is the same point. In other words, I am not picking up this point and place it somewhere else. It's the same point, but different way of representing its values or its location. So we basically, I'm repeating the previous sentence. True we have basically shown no information. That's why, Eric, we call it pretty good reconstruction. So the question is that, okay, we change our, let's call it coordinate, but what is this, what does this principal compound analysis do that this new coordinate is better? What is that it does is this. Which color? What it does is this. Okay, you are writing this. You cannot read my handwriting. You should not complain. But if you will, I can read it for you.
So, what?
This one?
No, the second line.
This one?
Yeah.
The same point. So we have basically thrown no information. Okay, write it. So what PCA do by finding this direction is this. If we are calculating all coefficient tucking, all these errors, undergraduate level tucking, these distances, if we calculate all of these distances, I don't draw all of them, and I add all of these distances are called error. And if I do it for all possible directions, we will see that principal component analysis will give us those directions which this one is minimum. So, here we are calculating the Euclidean distance, and we call it L2 error. So we are using lots of terms. What is the Euclidean distance that you knew from high school? We calculate what is the distance between this point and this point, this point and this point, and these points are the projected points that we have on this new line. So PCA also minimize this error, and this is very important because we will use this one in order to find out how we can reduce the dimensionality. So, can you tell me that what is the dimension of these black dots? Two. X, Y, right? Now, when I'm calculating the error, I try to find a line which has the closest type of distance with all of these points, right? So, can you tell me that when I'm talking about a line, what is the dimension of? 1. So, principal component analysis try to give us those directions that if from m dimension we go to the n, from n dimension we go to the m dimension, we have the minimum error. And m is smaller than n. So we are reducing the dimensionality and we are keeping this error to be minimum. So the fourth cool thing about PCA is
50.
Is it so? Yes. That was it. Minimizing L2 error, moving from n dimension to m dimensions. So if we have any line, and if we calculate the error, we will have the minimum error based on these lines that we have chosen. Now, this is initiating this idea into our mind that we have a good way of reducing our information, our dimensionality. So let's see how PCA will do it in a more better form. So PCA is finding a linear transformation that principally will not lose any information and minimize the variance, which, so no loss of information. The first thing was, the aim was minimizing the variance, now which results to maintaining distance as best as we can in any given dimension. So all those things that I have written, I have summarized those sentences in a paragraph. One of the very important thing, or maybe the coolest thing about PCA is that it has been formed, as I said, based on this IN problem. So it is all around the IN values. And why it is the coolest? Because IN value by its own is cool. And the properties that IN value are introducing to us are very useful. And because basically principal component analysis is these IN values and IN value decompositions, so we are inheriting automatically all the properties of the IN values. So let's talk about it and see how we are benefiting from that one. And actually, when we are talking about these IN values, we will start to see that how we can talk about the importance of these new dimensions. And when we are talking about the importance, we understand how some of the informations are not important, so we can get rid of them. In other words, we can reduce the dimensionality. If we have n dimension by PCA transformation, we still get n dimension, obviously, because we lose no information. Now, you may pick a subset M of them. By them I mean the new dimensions, the new directions. If you are lucky, n will be very smaller than n. This is the aim. If I have 1,000 features, reducing it by 1, it really won't help me, will it? But if from 1,000 you go to, let's say, 500, it significantly helps your process, helps you a lot. So, by subset, I mean some portion of this number of features. Here, we have 2. Subset will be only 1, right? But if you have 1,000, this subset can be like 400. On Friday, when we will go through the algorithm of PCA, how we can calculate many of these parts that we are talking about, hopefully by end of Friday I will assign you the homework, which inside that homework you will see, you will play with this number. You try to reduce your number of m as much as it is possible. Of course, can you tell me that if I am taking a subset and I am handling the data with that subset, what will happen? I lose information. So what is the consequence of losing information? It affects on my performance because I have less information. But the question is that if this information is a very vital information or it's not a very, very important information. Assume I am in a room and they tell me that there will be some incomings and these incomings are human. So I have to tick how many humans are coming in. Imagine if they reduce the information by there will be some incoming and just tick. And if there are some animals coming out, they start to tick. So you see, one of the important features, one of the important information is missed. So it results into something totally different. So PCA will help us which of those ends we have to choose. And in your homework, you will choose, you will play with this number and you will see its effect on the performance on the face recognition homework that I will assign to you. But anyway, let's continue in a very slight mathematical form. You will pick up the subsets n of these features, and hopefully this n is very smaller than n. It turns that associated with each of these new dimensions, so for each of these dimensions that we have in our example, and for each of these two dimensions that we have, dimensions that get is its IM value. So PCA will give us this dimension and will assign to each of these one IM value. That's why that knowing IM value is very important. Because if you know the properties of IM value, you know the properties of these directions. So PCA, you don't need to calculate it. PCA will do all of these ones for you. It will tell you what are the directions and what are the associated IM values to each of these ones. So here I will write a few lines about PCA, but it is actually the properties of the IM values. So if you are good in IM values, you will see these properties actually not belonging to PCA but belonging to IM value. And it is the IM value is guaranteed to be, what is the first thing that an IM value is guaranteed? To be limit. Tell me one important thing about IM value. Non-negative. What is the meaning of non-negative? Zero or positive. So it can be either 0 or a positive number. And so many other nice properties. They are very nice, believe me. More importantly, which actually lead us to the very solid conclusion. I write them in a separate word, but they are the same words. IM values are monotonically non-negative say that this is very important, more important than A? Why this is very crucial? What I want to conclude from this sentence? Eigenvalues are non-increasing.
So it decrease the set of data.
First, what does it mean? Non-increasing.
It's stable or
It's same or it is decreasing. Okay? So, for each of the direction, I am assigning one eigenvalue. So we step back a little. For this one, I have one eigenvalue. For this one, I have the second eigenvalue. Which one is first? The blue one is first. PCA tell me that this is first, this is second. So this has one eigenvalue, this one has another eigenvalue. What can you tell me about the eigenvalue of these two new dimensions? I have two eigenvalues. The blue eigenvalue is shown with lambda, and the orange eigenvalue. What can you tell me about these numbers? The blue has higher eigenvalue. Definitely, the blue has higher eigenvalue. We know that the orange one is at most equal to the blue one. Why the orange one cannot be bigger than the blue? Because this is the second vector, second direction, and we know that eigenvalues are not increasing. So it means that this is two dimension. If I have 100 dimension, so the eigenvalues, I have 100 eigenvalues, and the values are decreasing. The values are decreasing, 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 decreasing. So it means at some point, some of the eigenvalues start to become a very small number. So what does it mean?
Information.
I can get rid of them. Before killing some information, let's consider this scenario. What will happen if eigenvalue area is 0? It means that that direction is irrelevant direction. What is the meaning of irrelevant?
Doesn't give any possibility to discriminate.
Can you omit
What was the property number 1? For the cool thing about PCA, what was number 1?
So there's zero variance.
It has 0 variance. If eigenvalue is 0, it is irrelevant, which means that the variance is 0. But what is the meaning of variance is 0?
The value doesn't change.
The value is not changing. So if the value is not changing, can you Eric tell me, or Ozan tell me about the information? Variance is 0, value is not changing. What is the information? No. Of course, information is always constant value, it's value. So what is the value of information? We calculate the entropy. What is the value of entropy? 0. So can you see the sequence? It is not increasing, and it can be 0 because it's not negative. And if it is 0, it means that that direction is irrelevant from all these black dots that you have. Irrelevant means that the variance is 0. Variance 0 means that there is no change. No change means that the entropy is 0, so we don't have any information. That's the meaning of irrelevant. Now, I will try to write all these sentences. I have written them. I hope that I will be able to read my handwriting. And I can't complain about my own handwriting. It is like this. So it's not increasing. In other words, they tend to get smaller as you move from I's principal component. This means that we have to dismiss the class. But let me finish my sentence. As we go from the I's principal component to I plus 1's principal component. So PC means principal component. Now, if it is 0, we said it is irrelevant. And as we are Going down, and if we have higher dimension, these principal values will become smaller and smaller. Now, if the principal value or the ion value is very small, it means that the relevance of that direction to our data is very small. So if the relevance is very small, we can start to ignore it. So the principal component analysis will give us the direction, and we'll assign ion value to that one, which we look at the ion value, and we can do something which is called ignorability upon these new features. Now, if I have lots of small values, it means I can kill lots of these ones, and I can still get a very good way of representing my data. Of course, this time it will be lossy. If sigma value, if lambda is 0, there is no relevance, no problem. You can ignore the zeros. This is good case. But if the relevance is very small, you can ignore it. We will have a small error, but it will not be very big. It will not significantly affect on your performance. Of course, we have to continue about that one. We will do it on Friday. So on Friday for 10 more minutes, I will use the board. And then we will go to the slides. And in the slides, you will, on the slides, you will see that I have written something that download this MATLAB code. So you will go and download the MATLAB code. Although if you don't use MATLAB, we will go over that MATLAB code in order to tell you that how principal component analysis works. Because we don't, this is not a mathematics course, or not heavily mathematical course, so I don't want you to have a matrix of 1000 by 1000 and calculate the ion values. You ask computer to do it for you. It's important how to interpret it. We will talk about, the lines that we have drawn. Should they always pass through the 0, origin? Is it important that it passes through the origin?
No.
No. But we make it in a way that it passes through origin because it's easier to manipulate. And we will learn how we can do that one. We will talk about it. And if you have any question, keep that question. You can ask it on Friday after I finish what I wanted to talk. So you see, I have not tell you the mathematics behind it, although I will share the paper with you. We can find it from the module. These things that we have written is very important because it tells you to understand what is the PCA. So when you have a scenario, you can say that yes, PCA is a solution, or no, PCA is not definitely a solution. Okay, please stop the video.